Okay, so today we talked about flows on a line, and the idea is you have some differential equation first order, so it's first order ordinary differential equation in normal form without any explicit dependence on t. And what we can do is we can make a very useful graph which plots x prime versus x. So let's suppose that it looks something like this, that this is f of x. What information can we get about the function x from this? All right, remember, the goal of these differential equations is to find out about x of t. This is the state of our system. It could be a position, it could be a velocity, it could be the charge on a capacitor, it could be the population, it could be any number of things. Something that changes as time goes on. So this graph is going to help us learn about the unknown function. And here's the first thing that's helpful. These intersections. At these intersections, x prime is 0. We can tell from the graph. So nothing is happening. If the derivative is 0, nothing is happening. So these are all examples of equilibria. So the system is in equilibrium if nothing's happening. Now, what about between these points? Suppose we were right here, some particular value of x. And also let's call these something x1, x2, x3. So if we were between x1 and x2, so our system is between these two values, what happens? Well, x prime, the value of x prime, is given by going to the curve. Well, this part of the curve is below x prime equals 0. It's negative. X prime is negative. X is decreasing. So that means this point is going to move to the left. In fact, any point between these two is going to decrease. Any value of x here will, as time goes on, move towards a smaller value of x, because the x prime for that is negative. What if I were to the left of x1? Well, assuming my graph continues, then the value of x prime that corresponds to this value of x is positive. So it would increase in size. So look what's happening at x1. If you're to the left of it, you increase towards it. If you're to the right of it, you decrease towards it. This makes x1 what's called a sink. That's one way of putting it. Or you can call it an attractor. But we'll most call it a stable equilibrium. Things go towards it. If you're at x1 and I perturb you a little bit, you'll go back to it. What about x2? Well, let's look between x2 and x3. So what happens if we have our system take on a value between these? The derivative is positive. X prime is positive. So if I take a value right here, it's going to increase because the derivative is positive. So values that are around x2 flee. If you're a little bit smaller than x2, you're going to be dragged all the way down to x1. If you're a little bit bigger than x2, you're going to increase until you get to x3. What about for points that are bigger than x3? So x is greater than x3. The derivative is negative. Okay. Again, I'm not talking about the slope of this curve. I'm talking about this x prime. This x prime is negative. Right? So that means that x decreases. Right? X prime is negative. So it's going to go towards x3. So we call x2, you can call it a source. You can call it a repeller. We'll call it an unstable equilibrium. Because if you're close to it, you'll move away from it. If you're exactly at x2, you'll stay there. But any small motion around it, and you fly away. x3 is another example of a stable equilibrium. Now this information can be used to help us sketch a graph, and there's even a couple more. Notice that about here we have a max growth, and right about here we have, might say min growth, or you might say max decrease. Right? So if the first derivative has a minima, that's an inflection point in the graph of xt. If the first derivative, x prime, has a maximum, that's also an inflection point for this graph. Let me show you what I mean. Let's see if I can get. So let's try to sketch solutions. So x versus t. Notice the difference on the axes here. So I'm going to plot, let's see, let's do it right here, x1, and then we'll do an x2, and we'll do an x3. So those are perfectly fine solutions. They're constant solutions. If the system has that value, it doesn't do anything. Now, if we're between x1 and x2, the system moves towards x1. But does so in a very particular fashion. It has a steepest part about halfway through. So if I were to, sketch some solution, starting at x2, I have a very small decrease, and it grows. So it's very shallow, but then it gets very steep right in the middle, and then it levels off again until the derivative, x prime, is very small, meaning the curve, x of t, is very shallow and decreasing. If I start right in the middle, I'm going to start at the steepest, and then it'll be more shallow from then on. That is, I'll start concave up, and I'll stay there. Versus if I start closer to x2, I'll start concave down, and then go concave up. And we can draw a couple more curves here. So here are some sample curves. If I am to the left of x1, then my slope is going to be positive because I'm increasing, and I'm just increasing less and less. So, something like that. If I'm in between x2 and x3, then if I start close to x2, it's a small positive slope, and it grows towards the middle. So something like this, say. If I start in the middle, I'll have that highest slope. If I start closer to x3, it'll be shallow and positive. And say something like this, sort of halfway between. So what I'm finding here is essentially these inflection points of the graph, which I can locate. And if I can actually plot this function carefully, I might be able to find these things explicitly. So just imagine the power of not having to solve the differential equation, but being able to find the limits, find the inflection points, the concavity, where the derivative is positive or negative. It's a very powerful method here. So I hope this helps. I'll try to make another video with a specific application.